Okay, you'll have to excuse my voice. I've had a fairly severe cold for the last week. We still haven't quite got away yet. Like Lee said, I'm a bit of an unfortunate expert in this category, just having a career and working for Leica in Switzerland where I had to implement all transition curves for Europe, and found even there in their high-tech railway world that very few people there actually understood what they were using. And people were setting out spirals using completely wrong software and the wrong curve types. So I thought for this, since I've gotten off light at this conference and not having to do much, I said to Lee, maybe this is just a good short topic to go into. So, what are transition curves? And what are they? They are just simply a means of easing from a straight into a radius or between two radiuses. It's just a smoothing from going from one sort of curve to another. You've got two sorts. The sort from where you've got a straight road into a circular curve. That's typical for some road applications, and almost every single rail curve has that style of entrance. There's also the fitting of between two circular curves. That tends to be more rail work, where you've got existing railway track and they've gone and surveyed and matched up and found, well, this bit here is a 1,000 metre radius, but this bit's only 980 and we need to just put a curve to eat between these two. Who really needs them? Well, I've been pretty rude here by saying only railways. And that is because, yeah, if you've got the trains travelling at any sort of speed and you go into a curve, there's no give in the railway track, obviously. It's just a straight. You want some of the easing of the acceleration, centrifugal acceleration. Okay, what do they look like and how do we calculate them? They come in a mile of formulas. There are so many different formulas used around the world for them, it's not funny. But basically all the formulas allow us from the starting point of the curve to get a distance, x and y distance relative to the curve, and a deflection angle. And from there on we can do the calculations. I can hardly see that one, I'll have to look at the big screen. That is what they look. We get an x distance, a y distance, and a deflection angle. And from there, we can calculate positions and offsets along the curve. No rocket science involved whatsoever. And that's the other sort of curve we get, which is the transition. The blue curve is the transition between the two green ones, which are simply circular arcs. Obviously, these are all the V9 versions of the superline of doing all this work. Now, why are different formulae used? This is why this world of transitions is such a big mess. Transition curves predate computers. Transition curves predate computers by maybe 100 years. Like, people were building railways, if we know, from the 1850s, and they already knew then that they had to transition from straights into tight curves. So they had to be mathematically quite simple. As you can imagine, in the 1890s, calculations were not trivial. Big bunches of log tables or whatever else had to be used at the time. And yes, what they tended to do was, some mathematicians would sit there and pre-calculate all these little x and y's we saw before for various curves, and the designers would just use fixed lengths, fixed radii, etc. So at least the surveyors had some hope in the field of setting this stuff out. Then, computers in the office predate computers in the field. By the 1960s, 70s, designers had computers, but surveyors didn't. They were still using primeval sort of tools to do it. So this obviously meant that the designer in the office could design some quite sophisticated curves, far more than the surveyor in this field could actually set out with. This led to the next big problem, that approximations were started to be used by surveyors in the field. To okay, well, this curve only goes through 5 degrees, so if we use this formula, then that's good enough for what we actually have to set out. And as I'll allude to a little bit later, this has subsequently been confused with being real curves. So you've got this situation these days where people think that this old surveying approximation is actually what the design is. And engineers being engineers, everybody thinks they can design a better curve. And that is very much the case in rail design. There's been all theoretical curves and bits and pieces, and it's just led to this plethora of designs. Okay, the classic curve, what we call the natural clothoid, both Euler spiral, Fresnel integral, etc., etc. It's been around, the mathematics has been around for a long time. Mid-1800s, I think, something like that. But it's a true spiral. It's where the radius is proportional to the length along the curve. the sideways acceleration is a constant. So it's like a vertical curve, a parabola, but the rate of change of grade is a constant. With these spirals, the rate of change of sideways acceleration is a constant. It's theoretically an ideal transition curve. I say theoretically because it doesn't take into account the cant of the tracks. So in the rail curve, as the tracks scratch the cant, that obviously changes the position. So it's not actually a perfect curve, but it's a very good sort of curve. It's an ideal curve for a computer to calculate. It's not so ideal by hand. We have this basic little constant, that the radius and the length along the curve are constant. That is what defines a clothoid. However, it gets a little nastier after that for doing it by hand. Everyone who remembers their high school mathematics, hopefully you went to that mathematics in high school, but we have a very simple formula for calculating the deflection angle, but unfortunately those x and y components require evaluating those integrals. Mathematically it's very simple, but by hand it's obviously a bit of a nightmare. And that is what the actual clothoid looks like. It's a curve that just goes from a straight and just continues to translate, rotate into that small point in the middle. What happened? The clothoid was obviously too complex. It couldn't be calculated by hand, but the mathematics were around a century ago to easily expand these curves out. Most people worked out they adopted curves based on the accuracy they needed. For typical road or rail transitions, you rarely see a curve that would have a deflection of more than 5 degrees. So most of the authorities, such as Main Roads, adopted these power series expansions that would work up to about 45 degrees. And as you see, they're not rocket science mathematics at all, they're just a very simple formula. So, what formula are used and where did they come from? In Australia, we have the clothoid, and we had to distinguish this between the clothoid and the natural clothoid for V9, because the clothoid is the term used here, and it is not that previous object you saw that looped into infinity. It is simply the first bit of it from about the tangent point to about 45 degrees in that the formula holds up for. After that, its bets are off. It is not a true clothoid. There's the Restoral cubic is used in Western Australia. It's also a clothoid-based formula. It's designed for our work, and it's designed the fact that they know they need to go no more than 15 degrees or something into the curve, and it's all good. In New South Wales, they use the cubic parabola. I'll go into these just a little bit more later. It has nothing to do with a clothoid. It is an actual. It's different. We'll look at it, but again, it's clearly defined as what it is and how to use it. Worldwide, in some places they do use that true clothoid, and we'll elaborate on that a touch more later. In Germany especially, they use a curve called the Gloss curve, which is based on the properties of the natural clothoid. A very clever engineer in the 1920s, 30s took into account the cant of the track and what it should look like, and he came up with this derivation. The Wiener Bogen, I think it might be Bergen actually, I can't remember my German very well. It's a rail curve used in Austria. It's a heavily engineered curve where they went and looked at existing rail tracks and made all theoretical adjustments about with the cant and the loading of the trains on the tracks, and they came up with this curve, which I believe has proven to be in real use far less wear and tear on the rail. Again, we don't use that in Australia, and it's a highly engineered curve, lots of numbers and formulas. Again, fine for computer, but a nightmare by hand. And then you have these other derivations, the sinusoidal curves, so cosinusoidal, blah, 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 blah. They're just various places decide they really want to use one of these rather than the standard stuff. What formula aren't used? Well, the classic is, as I was talking about before, the so-called cubic spiral. In 99% of cases in the world, it is a misunderstanding of the old surveying approximation of clothoid. And I've seen this all over the world, including France and Spain for the railways, where these people told me, no, this is the curve we used for rails. And I sat there and they gave me numbers out of InRail or somewhere with all it, and I tried to get it to work, and this never did. It was always millimetres, 2 millimetres, 3 millimetres. And finally I got, okay, I'll just put these numbers into a clothoid. And lo and behold, it worked perfectly. So even in these rail engineers there didn't even understand. They still looked up their 1970s textbook on an approximation to a clothoid, and then when they'd gone computerised, they still put this approximation in instead of just using the real thing. And that's a bit what this talks about. There's just such a misunderstanding at times on these curves. Now, the other one that is not used in the world, even though engineers do use it, but it's illegal, is the natural clothoid. Because very few authorities, if you look at your documentation, it will be a limited term of that power series that we saw. It expanded to 4 or 5 turns. It is not the natural clothoid. It is a completely different curve. The clothoid, again, is a very good approximation for the first, from a straight into, say, 15, 45 degrees, but after that, it spirals off into the distance. It's not a true spiral. So, in 12D, what do we have? We've got the clothoid, and that's as specified by the Australian, most Australian road authorities, Queensland Rail, etc. It's a limited term expansion of the clothoid, typically I think 4 and 5 turns for the X and Y values. We have the cubic parabola in New South Wales. Again, it's a specific formula, it's clear, it's well specified. And also the rest rail cubic, which is another, said before, another definition of clothoid. It's a very clear specification. The cubic spiral, I put a question mark there because we have it in there. It's the land XML definition of the cubic spiral, but it's just not used here. I can personally remove it out of the menu, but that's for everyone else. The natural clothoid, we fully support it. We did a lot of mathematics and engineering for the curve fitting, so this would work very quickly, but the only thing is you really can't use it. The Bloch curve, as by Deutsches Bahn, is in there. It's the genuine Fertig deal that the German railways use. And again, we have some of these other definitions out the land XML manual for sinusoidal, co-sinusoidal, etc., etc. But remember, the only ones actually used in Australia are the clothoid, the cubic parabola, and the west rail cubic. Quick reminder, the 12D clothoid, or the clothoid as specified by most of the road authorities here, is a simplification of the true clothoid. And it uses 5 and 4 terms of the power series, and again, it's not a true spiral. It doesn't loop into itself like that. It goes a little bit like that, then it just wavers off in the distance like your normal mathematics functions. Again, as you see, it's not rocket science material, the mathematics behind it. There's just clear definition, very simple calculation by computer. The cubic parabola, as used by New South Wales Railways, it's not clothoid at all. It's not a spiral. It's your old y equals mx cubed that you did at school when you were in high school. It's valid to about 27 degrees, so it's actually it's a curve of tightening radius to about 27 degrees, and after that the radius starts to increase again. So along the main style, most of the authorities, like I said before, realised that they only needed spirals that were good to 15, 20, 45 degrees, and that was the specification that they put in for them. Surprisingly, these cubic parabolas are computationally quite expensive because while we have a deflection angle defined, which is very simple, you'll notice in the little other formula, y equals mx cubed, we don't have any specific relationship with the arc length to the values that we need to set out. So we actually have to do an iterative solution to do it. That's just a... Okay. Can you mix and match these beasties? The simple answer is no. If you're working in Western Australia, then you need to use a west rail spiral. The curves in Australia are clearly defined, unlike some places in the world, such as the mess that land XML definitions of spirals are. Too generalised. They are a specific formula used here. The offsets between the different transition curves get progressively larger. So if you try to go from a transition curve from 60 metres long to 0 to into a 400 metre radius curve, it's not the same. You cannot use these different spiral types to mix and match. The consequences can be quite disastrous. Yep. So on curves where the offsets are similar, yes, sometimes the geometry is quite funny. The actual difference between the two arcs in day is quite small. However, the tangent points vary quite significantly. And unlike roads, a train pulling into a station has a lot tighter tolerances, and I think we'll let Alistair just to fill us in on that one.
I don't have to speak on the mathematics, that would have really killed me. Probably one of the things that we're talking about here is with, if you get a situation where you've got a station platform and a curve, which is not ideal, but sometimes does happen. We've got the very small gap that they allow, so that where the train doors open, the gap between the platform and the door is normally in Western Australia only allowed to be 50 millimetres or less, so anyone in a wheelchair or anything like that, they're not going to get a wheel dropping through those things. So by using different spirals, which are not allowed, but if you had a look at say, a Clothoid as opposed to the West Rail Cubic, on smaller radii curves, then the gap between the platform and the edge of the train would, and it also got down to a certain case where a line was designed using the incorrect curve, and it turned out that the front of the train would actually have hit the platform as it came in. So the effects that we're getting with those spirals, certainly on the tighter radii, become more and more increased. On the larger radii, you wouldn't see it quite as much, but it's critical for the overhang on the front of the train and also on the gap on the side of the train to the platform.
Alistair was rather nice there. A consultant actually designed this railway and refused because their package didn't handle the West Rail Cubic, and if they'd frigging constructed it, the railway would have gone straight into the platform as it went into the tunnel. So if you get these things wrong, they would have been sued well and truly because they just would not believe that the West Rail Cubic was not some other thing that they had available in their package.
I guess one other thing as well was that we were getting calls back from surveyors saying, well, this is not correct geometry, and again it was purely that they hadn't been defined as to exactly what was going on, and their instruments weren't accepting the particular spirals that we were putting in, so we had to give them the definition, and then they were happy that it was a real spiral.
Yeah, so that was just one that we emphasised the point that people just think that these things are the same when they're not. And yes, if your software can't support it, then yes, by 12D. Okay, go in the right direction. Helps when you do that one. And just a little final one, arc-to-arc fitting. So this is this case, it's mainly railway realignment, where as I said, you'll go and survey and they'll find, well, this bit of track matches a 1,000 metre radius and this one's only 980, so we want to put a little bit of curve in between them. And that's why. It's mainly railway realignment, not greenfield design, because there you just need a classic straight transition, arc transition, straight sort of design. Okay, which types of spirals can you use? Transitions curves I should use, sorry, because we don't actually use spirals as such in Australia. Which types can do it? Easy answers, all of them can do it. However, the Clothoid, as specified here by rail and roads, the Cubic, Parabola in New South Wales and the West Rail are very limited in their arc-to-arc fitting. And this is because there are only certain mathematical situations where you can get a curve with a radius here and a radius there at a portion along the curve that match up. And I've seen the pain personally that New South Wales railway designers go through trying to fit an arc-to-arc cubic parabola. They spend hours just jigging a little bit here, a little bit there, until they finally get a curve magically appearing. And I don't know how much the situation's improved, but it is actually very difficult. And if anyone's played with a super alignment with a Clothoid in 12D and V9 and just picked an arc here and an arc there and try to fit a spiral between it, you'll probably find 9 times out of 10 it won't. And that's the reason, because it can only fit from that infinite radius point through to about 45 degrees or something. If the two curves don't magically match something in there, it can't be done. The natural Clothoid is particularly good at fitting arc to arc. But funnily enough, sometimes the answer you get is not quite what you expect. Here we have a typical example. I just drew 2 arcs up inside 12D and fitted the natural Clothoid. And as you can see there, you get that beautiful line fitting from one arc to the other. Again, you can't do that with a Clothoid because the Clothoid's only valid to about 45 degrees at best. And as you notice here, that curve is quite long. Unexpected. I just drew up another 2 curves. Now you think you could fit a natural Clothoid between these, no worries, wouldn't you? You can. However, the answer's probably not what your engineers are going to want, or you might be wasting a little bit of pavement, because that's what happens. So that is a perfectly valid natural clothoid, but yes, sometimes even they don't work, and you will get this. It's quite amazing when you've got two similar radii, this situation can actually happen quite a lot. And that was the end. So hopefully, just wanted to make something, make things a little clearer on what transition curves are in Australia, what you can do and what you can't do. And that's it, thanks.